Hello Nadir. Uh, so I thought I'll make a video on ideal gases now, and we'll start this and we'll try to do this as a purely online thing, and then maybe we can meet for questions. This one, what I was thinking is in this particular video, we'll just cover till uh, 20.6, and then the last two equation because it diverges. After that, a little bit into the kinetic model, so that we can cover in a separate shorter video. So this, like in a nutshell, if I tell you, this we have already been doing for a long time, and this is just in a way a lot of it is just summary. So hopefully we can get through it quickly, and at the end of the day, till 20.6, what we are going to get to is uh, just a single equation, which is called the ideal gas equation, which we have already studied, but we'll just do this as a quick revision. So let's get started. So the first thing that we need to know about gases is they move, like they are small particles that move very, very quickly. So something like that is very important to understanding of a gas, and these particles move very, very quickly. So one thing that your book mentions is they move at about 400 meters per second, uh, which is incredible because 400 meters per second, if you convert it into kilometers per hour, let's try to do it. Yeah, that's a lot, right? Yeah, so they go very, very fast. So it makes it even harder to kind of track them in a way. So what we do in here is something called macroscopic versus microscopic properties. So the idea is macroscopic is all that you can observe on the outside, which is something like pressure, volume, temperature, which are these things on the outside. But say like velocity of particles, kinetic energy of particles, forces between particles, right? So when a particle is concerned, a single particle inside a gas chamber is concerned, anything to do with this one particle is we can call it a microscopic property. uh, but then the whole thing on the whole is macroscopic. So pressure is observed on a wall uh, of a thing, right? It's not observed on a small particle. We say, okay, what is the pressure on the hand, what is the pressure on a particular area, right? Volume is a macroscopic property. We don't talk about the volume of one particle, we talk about the volume of the whole chamber, right? And temperatures of the whole gas. So this whole concept is kind of, we can say, macroscopic, right? So the topic that we'll talk about in the second video will be to connect these two. So we'll get into that. But first, let us understand what all can we observe practically, right? So, like gas is one of the earliest things that people see in 1600s. A guy called Boyle, so it comes from Boyle's law, right? So this guy observed that, okay, if I put a gas in a chamber, uh, and say there are particles here, and then the gas is at say temperature T, then I so say there is a piston here, right? And you say push the piston in, right? And you get to this point where the gas is compressed, but the temperature is still equal to T. In that case, you will notice that now it takes a lot more pressure to kind of hold it there. So we can say that the pressure on this has increased, right? So it's the same idea. So you have decreased the volume, so pressure has increased. So like that kind of gives us a picture about what the pressure is coming from. The pressure can come from two places that a book mentioned. It can come from the number of particles that are hitting the wall, and the other source that it can come from is the speed of those particles. Speed plus mass, like what we can combine it into a single factor, that's the kinetic energy of each particle. So these are the factors that are responsible. So let's go through them quickly. So one of the things is how fast a particle is going. If the gas is moving faster, so the way to make them move faster is to increase the temperature. If the gas was say hotter to begin with, then the speed would be higher, so the pressure would be higher, right? Something like that. Other thing is if say we had a heavier gas at the same temperature, then they are moving uh, like faster, say, and then the heavy particles, so when they bounce off, so they are exerting a lot more punch every time they're hitting the wall. And the last thing is the number of particles. So if there are 50 particles instead, so you fill a lot more gas in that same area, so that will also cause a lot more pressure. Again, these are just simple things that we understand, but it's always good to kind of put them in front of you so that you can think about them clearly. Anyway, so now that you understand what pressure is, what Boyle observed is this same pressure increases when it decreases the volume. So from what he found was, so he wrote it in different forms. So he said that pressure is inversely proportional to volume. So increase in volume leads to decrease. So increasing in volume decreases the whole fraction is 1 by 10. It decreases this pressure, right? So this is the another way of writing. Another way of writing the same thing is PV is a constant. So every time you have a pressure value, you have a volume value, and in the second scenario, you have a pressure value and a volume value. So P1 V1 is equal to P2 V2. This will always be that same constant. So this is what Boyle found, which was an interesting conclusion already. So one of the ways that we can kind of talk about it is this graph that you talks about. So it kind of looks like this. So, so notice that this is a pressure and volume graph. So if P is proportional to 1 by V, so it is kind of like pi is equal to 1 by x. And say this gets converted into P is equal to K by V. K is where like the constant of proportionality. Then this kind of looks like K by x, 2 by x graph, right? And you know 1 by x graph looks like this. This is one way to look at it, or the other way to say is okay, I want to plot 1 by V instead of V. So the same thing. So your 1 by V here becomes like a parameter like x. So it just becomes in the form y equal to kx, right? In that case, y equal to kx is a straight line that looks like somewhat like this, right? Anyway, the bottom line is this PV equal to constant, this relation that we started with holds, and it can be represented through these two diagrams. So this is what Boyle found in his study. Okay, now the other thing that we'll discuss, the second thing is called Charles law. So this other guy Charles, what he observed instead, so he observed that if you decrease the temperature of the gas, then its volume starts to shrink. So it's like you're cooling the gas down, so kind of the volume starts shrinking, right? So what he observed is, say the volume was at a certain point for a certain temperature, that volume started to go down. Say when he lowered the temperature from T1 to T2, it went down from V1 to V2, right? So something like this started happening. So, so he also kind of quantified that relation, saying that volume is directly proportional to temperature, right? Okay. So there are two things here. So first thing is we can uh, try to combine this with what we know already. So we know pressure is this, so which we can also write it as this from Boyle's law, and we at the same time know that from Charles' law V is proportional to temperature. We can combine these two equations and say that volume is proportional to temperature by pressure, right? And then simply we can say that uh, V equal to some constant, hence temperature by pressure. So that makes it PV by T is a constant, right? So which again is the same way of saying that P1 V1 by T1 is equal to P2 V2 by T2. So for a gas with like constant mass, which is the case in all gases, this is true. So this is kind of like a gas equation, right? So this is one thing that we can see from here. So this is combining Boyle's law with Charles' law, right? Okay, and so that's one thing. And the other thing that we see from Charles' law is, so he said that, so let me take the help of a book here. So what he noticed is something like this. It looked like the volume was decreasing from this point to this point as the temperature was decreasing. But he said that if it is decreasing linearly, in that case, I can extend it to say that at what temperature does the volume become zero. So this is also a special concept. So this is called absolute zero. So this happens at minus 273.15 degrees centigrade, or which is exactly 0 Kelvin. So that's how we define what a zero of a Kelvin scale is. At this point, basically, theoretically, the gas has zero volume. So you start cooling it down, it starts shrinking, and at some point it gets zero volume. But you can imagine that all these particles can come only so close, and when they sometimes come so close, they stop becoming a gas, right? When things become too close, they either become a liquid, and then when they become even more close, then they become a solid, right? So this is kind of like a theoretical concept because we know that it will stop being a gas. So the here is where we break we bring a distinction between real gases versus ideal gases. So real gases have this fall off basically. It's like they'll follow this curve till a point, and then all of a sudden around say 200 or 196 for nitrogen, it falls off. Like it basically, and at this point it has become a liquid. It stops following this curve, this gas equation sort of thing, this Charles law equation. Yeah, so that's the core idea behind the gas equation here. So this is what they show. I highly recommend reading the book for all of this. It shows a very nice, clear picture. Uh, okay, and then we can start to combine all the equations. So the whole ideal gas equation, you know that it has this form PV equal to nRT. Again, this is comes from the same thing as PV by T is some constant, and that constant now we are just saying is equal to nR, where n is the number of moles. So moles is important. It's not mass, it's not number of molecules, it's number of moles. You should remember how to calculate it, and this is just what you call a gas constant at a fixed value of 8.314, right? So that's just a constant. So something like this is very straightforward. Another way of writing the same equation, which you might not know, which we'll see more in the next part of this lecture, which will be equal to nkt. So this nr, this constant is something else, nkt, but this n is not little n, but this is a capital N. So here this is number of molecules, and here instead of the gas constant, it's what we call Boltzmann constant. it also has a fixed value, um, but I don't remember it on top of mind, but it's really small. Um, so it's something like, yeah, they don't give it here. I probably they give it on some other page. But yeah, we'll discuss this second equation more in depth in the second one. But then both of these are basically equivalent, basically the same thing, right? So we'll talk about what they mean. Meanwhile, you should try to do all the questions till basically till here, till 12, including the worked examples. They are just practice. I know that you know, but it will be good practice for you. And then in the next part of this lecture, I'll continue with 20.7 and 20.8. Okay, see you. Bye bye.